Welcome back to another lecture on rings and ideals. In the previous lecture, we have defined a prime ideal as well as a maximal ideal. In commutative algebra, prime ideal plays a very important role. So we will be proving the existence of a prime ideal in a ring, where a ring shall mean a commutative ring with identity as noted earlier. In the next theorem, we will be proving that every non-zero ring has a maximal ideal, which in turn says that every non-zero ring will also have a prime ideal, because we already noted that a maximal ideal is always a prime ideal. Before going to the theorem, we will quickly go through some of the concepts that we need here. Especially, we need a result which is known as Zorn's lemma. The theorem is going to be an important application of Zorn's lemma. So we will quickly go through some of the required results. First of all, what is a poset or a partially ordered set? A partially ordered set is a set, a non-empty set P, together with a relation, usually denoted by less than or equal to, such that for all A, B, C belonging to the set P, the following three conditions must be true. First one is A is less than or equal to A. Second one is A less than or equal to B and B less than or equal to C must together imply A is less than or equal to C. And the third condition is A less than or equal to B and B less than or equal to A must imply A is equal to B. The first condition is referred to as reflexivity, and the second one is the transitivity, and the third one is antisymmetry. So a relation which is reflexive, transitive and antisymmetric is referred to as a partial order, and a set together with the partial order is called a partially ordered set, or simply a poset. We have written some examples here. The first example would be the set of all real numbers with respect to the natural ordering. That is, we say that two real numbers A and B satisfy the inequality A less than or equal to B whenever B minus A is non-negative. With respect to this relation, R forms a poset. Second example is, if we consider the set of all natural numbers with respect to division, it also forms a poset. And we can take any non-empty set X and consider its power set, that is P of X. It gives us a poset with respect to set inclusion relation. Now we will define what is called a chain in a poset. If P is a poset and if T is any non-empty subset of P, we say that T is a chain in P if every pair of elements in T are comparable. That is, for every xy belonging to T, either x is less than or equal to y or y less than or equal to x must hold. So a subset T of a poset is called a chain if x is less than or equal to y or y less than or equal to x for every xy belonging to T. An example would be, you can take any non-empty subset of the set of real numbers with respect to the natural ordering. Any non-empty subset would give a chain, because in R we know that every pair of real numbers are always comparable. Let P be a poset and T be a subset of P. An element X belonging to T is called a maximal element if there is no element A in T such that X is strictly less than A. Next, we'll define an upper bound of T. Let P be a poset as before and T be a subset of P. An element X belonging to P, note that X need not be in T here. An element X in P is said to be an upper bound of T if X is greater than or equal to all elements of T. That is, X is greater than or equal to A for all A belonging to T. At this point, the learner could try to make out the difference between the two definitions, keeping in mind that in a poset, two elements may not be always comparable. Look at the two examples here. The definitions will be clear to you with these two examples. As a first example, I have considered the set of all natural numbers with respect to division. as a poset P, and I have taken T to be the set containing the numbers 2, 3, 5, 8 and 10. For this subset T of n, with respect to division, we see that the numbers 3, 8 and 10 are maximal elements. All these three elements, 3, 8 and 10, are maximal elements of T. And 120 forms an upper bound of T with respect to division again. You see that to be an upper bound, this number should be divisible by all the numbers given in the set T. So 120 is an upper bound. You can come up with any other multiple of 120 which will also give an upper bound of T. Now we will consider the same set T but in another poset, that is in the set of real numbers with respect to natural ordering. I have considered the same subset T, and in this poset we see that 10 is the only maximal element of T. 10 is the only maximal element of T with respect to natural ordering, and you can take any real number greater than or equal to 10. It will give you an upper bound of T with respect to natural ordering. Next, we will state the Zorn's lemma. The concepts that we have defined so far will be used in the statement of Zorn's lemma. That's why we have defined all these. Zorn's lemma states that if every chain in a poset P has an upper bound in P, then the poset P must have a maximal element. If every chain T of a poset P has an upper bound in the poset P, then P must have at least one maximal element. This is what the Zorn's lemma states. Keep in mind, Zorn's lemma is taken as an axiom. There is no independent proof of Zorn's lemma, but it is always possible to see that Zorn's lemma is equivalent to the well-ordering principle as well as to the axiom of choice. To know more about Zorn's lemma, you can refer the book titled as Naive Set Theory by P.R. Halmos. We shall prove the theorem which states that every non-zero ring A has a maximal ideal, which is one of the standard applications of Zorn's lemma. We will prove this theorem now. Let A be a non-zero ring and let S denote the collection of all proper ideals of A. As A is given to be non-zero, we can easily see that zero ideal will be a member of S, that says S is non-empty. Now we will consider the set inclusion relation on S. Then you can easily verify that S with respect to inclusion forms a partially ordered set. That is, you need to verify that inclusion is reflexive, antisymmetric and transitive in this collection S. So we have a poset now, that is S. Now we will prove that in this poset S, every chain has an upper bound. Every chain has an upper bound, and then we will be applying the Zorn's lemma. So the claim here is we will prove that every chain in S has an upper bound in S. Let us take a collection of ideals, that is collection I alpha, to be a chain in S. So collection I alpha is taken to be a chain in S, and let I naught denote the union of all the ideals present in this chain, collection I alpha. We will take the union of all the ideals in this chain I alpha and will denote it by I naught. Then the set I naught forms an ideal of A. Again, using the definition of an ideal, verify that I naught forms an ideal of A. Also, this ideal I naught is not equal to A, because I naught is a union of all I alphas, and because collection I alpha is a subset of S, you see that each I alpha is a proper ideal of A. So I alpha is not equal to A. That says 1 does not belong to any of these I alphas. Identity element is not in any I alpha. So that 1 does not belong to the union, that is I naught also. So I naught is not equal to A. This says that I naught is a proper ideal of A. Further, each I alpha in the chain is contained in I naught, because I naught is just the union of all the I alphas. So each I alpha is a subset of this union that is called as I naught. That says I naught forms an upper bound of the chain I alpha we have taken in this poset S with respect to inclusion. Thus, we have shown that I naught is an element in S which acts as an upper bound of the chain I alpha which we have taken. Since the chain collection I alpha is arbitrary, every chain in S has an upper bound in S, and now we can apply the Zorn's lemma. And by the conclusion of the Zorn's lemma, S must have a maximal element, and we will be calling this maximal element as M. Let M denote a maximal element of S. Since this maximal element M belongs to S, by the definition of S, it follows that M is also a proper ideal of A. Further, if I is any ideal of A such that M is contained in I and I is contained in A, then it must happen that either I is equal to M or I is equal to A because of the maximality of M in the poset S. Because M is a maximal element in S, then we must have either I is equal to M or I is equal to A. Otherwise, it will contradict the maximality of M in the poset S. That is, the fact that M is a maximal element will be affected if I is strictly lying between M and A. This says that we cannot find an ideal I which strictly lies between M and the ring A. And we also observed that M is not equal to A. So we can conclude that M forms a maximal ideal of A. Thus, we have concluded using the Zorn's lemma that every non-zero ring A always has a maximal ideal. Next, we shall discuss two corollaries of the theorem which we proved just now. The corollary 1 states that if I is a proper ideal of a ring A, there always exists a maximal ideal of A containing I as a subset. Equivalently, we can state that every proper ideal of A is always contained in a maximal ideal of A. Let us start with a proper ideal, say I of A. As I is not equal to the ring A, if we look at the quotient ring A by I, it is a non-zero ring. And we also know that whenever A is a commutative ring with the identity, A by I is also a commutative ring with identity. So we have the quotient ring A by I, which is a non-zero ring now. If we apply the previous theorem to the quotient ring A by I, this ring A by I must have a maximal ideal. We shall call it as M bar. Now we will be considering the canonical map or the canonical homomorphism, which we have already noted earlier under homomorphisms, denoted by phi, which is from A to A by I, given by phi of x equal to x plus I. If we make use of this map and apply the correspondence theorem for rings, we see that the inverse image of M bar with respect to the homomorphism phi gives a maximal ideal of A containing the ideal I as a subset. Thus, we have justified that every proper ideal of A is contained in a maximal ideal of A using the previous theorem. Let us look at corollary 2. Corollary 2 states that every non-unit in a ring A is always contained in a maximal ideal of A. An element which is not a unit is usually called as a non-unit, an element which doesn't have a multiplicative inverse. So we are proving here every non-unit is always contained in a maximal ideal. That is, a non-unit is present as an element in a maximal ideal. Start with the non-unit. Let X be a non-unit in a ring A. Then look at the ideal generated by X. We have noted under the section ideals in the beginning that an ideal generated by X is equal to A if and only if X is a unit. As X is a non-unit here, ideal generated by X is a proper ideal of A. And now if we apply the previous corollary, corollary 1, we see that this ideal, that is ideal generated by X, must be contained in some maximal ideal of A. And if the ideal generated by X is a subset of M, then of course the generator X will also be in M. That says we have found a maximal ideal which contains this non-unit as an element. Thus we have justified that every non-unit in A is always contained in a maximal ideal of A. Next, let us look at the definition of a local ring. What is a local ring? We call a ring to be a local ring if it has exactly one maximal ideal. A ring having a unique maximal ideal is usually called as a local ring. You can think of any field as an example here, because a field has only trivial ideals, zero ideal and the whole field itself. Then you should be able to realize which is the only maximal ideal, so that every field gives us an example of a local ring. After defining what is a local ring, now let us look at a proposition which gives us two simple conditions which will conclude a ring is a local ring. There are two parts in this proposition. First one says that if A is a ring and M is a proper ideal of A such that every x in A minus M is a unit in A, then A is a local ring with M as its maximal ideal. And the second part states that if A is a ring with M as its maximal ideal such that every element of 1 plus M is a unit in A, then A has to be a local ring. First we shall prove the first part of the result. Assume the given hypothesis that M is a proper ideal such that every element in A minus M is a unit in A. Let us look at any proper ideal I of A. Consider an element x from I, then x cannot be a unit in A, because once x is a unit in A, the ideal I will be equal to A, which is not true. Therefore, x is a non-unit in A. And since x is a non-unit, it cannot be in A minus M, because our hypothesis says that A minus M is containing only units in it. So x is not in A minus M, or equivalently x belongs to M. Thus we have shown that every element of I belongs to M, or equivalently I is contained in M. Thus every proper ideal of A is always contained in M, which says that M is the only maximal ideal of A. Thus we have proved A is a local ring having M as its maximal ideal. Come to the second part of the result. Let A be a ring with M as its maximal ideal such that every element of 1 plus M is a unit in A. We will be making use of the first part of the result here, that is, consider any element x from A minus M, or equivalently x is not in M. Now if you look at the sum of the two ideals, M and the ideal generated by x, we will be looking into the sum of ideals concept later in details. Remember at this point that sum of two ideals also gives an ideal. So M plus ideal generated by x is an ideal of A, and it contains M as a subset. Thus we have an ideal M plus ideal generated by x lying in between M and A, where M is maximal. But M cannot be equal to M plus ideal generated by x because x is not in M, whereas x belongs to M plus ideal generated by x. So the only possibility, because of the fact that M is a maximal ideal, is that M plus ideal generated by x must be equal to A. Because 1 contains the identity element, we can write 1 is equal to M plus AX for some M taken from the ideal M and some A belonging to the ring A. Rewriting this equality, we can get AX is equal to 1 minus M, and 1 minus M is an element from the set 1 plus M, because remember minus M is also an element in the ideal M. So we have AX is a unit in A by our hypothesis given in 2, and if AX is a unit in A, we can easily observe that the element X also forms a unit in A. Thus we have shown that every element of A minus M is a unit in A. And using first part of the result, we can conclude that in this case A must form a local ring.